Okay, well, welcome everyone. Thank you, Dr. Harris. We are here to present Group 1's project, the 192-inch Flask Lifting Safety Jig. It's our final presentation. I'm here with the other members of Group 1, John Spears and Reggie Hilton. They're each going to have their own distinct section of the presentation. I'm going to bookend it on the front and the back end of this, and I'll start off with the agenda. So the agenda for the presentation tonight, we're going to go through the background of the situation. We'll talk about the problem we're trying to solve. We'll go through and review our goals and objectives, risks and constraints. John's going to go into solutions, research, and talk about the methodology and the design criteria and the design of the jig itself, and finish up with materials and equipment and deliverables. We'll go through implementation plan and criteria for success. And Reggie will talk us through the prototype, the finite element analysis and testing. You'll get to see the jig 3D model and the Flask 3D model tonight. Reggie's going to show us those. And then on the back side, I will finish up with talking about the project timeline, the extension that occurred during the project, and then also the financial outline and the return on investment for this project. So the background, our business partner, GWI Industries, they're a producer of some of the world's largest slurry pumps in the world. This one that we're talking about is 192 inches square. And you can see the picture to the right, what we're talking about. It's a very heavy object, 40,000 pounds, roughly. It's difficult to move around the facility. A crane, an overhead crane that you saw on the first slide with the opening slide, is what that moves that around inside of the facility. And our topic for this, our target for this project, was to be able to get it to move outside the facility where the crane is not available. There are multiple flasks. 6 flasks are actually stored on the process floor within the facility, which is part of the extension of the lead time that we're going to talk about, and the difficulty that the company is facing with extended lead times, lack of processing ability, and space. Those 6 flasks that I mentioned before, they take up approximately 3,000 square feet of valuable floor space. And the casting must sit inside that until it's able to go through the shakeout process. And that shakeout process can't happen until there's room to maneuver the flask to the correct location. So these six flasks sit on the floor and aren't able to move until the next one is needed to continue the next process, which elongates that lead time. When we look at the lead time, it can sit on the floor for up to 6 weeks. And the objective of this project was to reduce that by 2 weeks, resulting in an approximate realization, I'll call it, of new revenue or extra revenue of $2.08 million. So that we're calling a lost production value. If we were able to move these flasks correctly, move them out to the yard, that we were able to get the parts out, the lead time would shrink, and we'd be able to make much more parts to the tune of 2 million plus. So the problem to solve, and I'll just review it a little bit again. We don't have a current process that's EHS approved or safety approved that is able to get those flasks out of the yard. And you see a picture on the left here where the flask is being walked out by a fork truck or powered industrial vehicle. And they're picking it up by a chain and they're walking up the front end, moving it, dropping it, walking up the front end, moving it, dropping it. And it's time consuming, it's not safe, it's not approved. There's no jig or fixture that we have today that allows the team to be able to do that on site. So getting the flask from the threshold to the yard, the storage facility or the storage yard, is paramount to make sure that this project finishes correctly. So goals and objectives, the main thing that we're looking for is to reduce that lead time. That lead time leads to realizing more revenue for the company. And to do that, our objectives are passing result from SolidWorks FEA, which Reggie will cover. We needed to receive approval from the safety team and fabrication team, which we did. successfully implement the completed jig. We'll talk about how we're delayed on that, but we do have a recovery plan, and we've been working towards that. And then identify any further improvements to the jig or process that can be implemented in the future. Reggie's going to hit on some of that tonight, and then there's going to be some that's done later through John and his team once the fabrication process is completed. Risks and constraints. We've closed out everything except for a major and what I'll call a catastrophic risk from a project completion timeline. Our goal to complete was April 25th, essentially yesterday, for this project to complete on time. Based on the cost of the project and a new or misunderstood process, however you want to look at it, from corporate at GWI, we needed to go through a further process, financial approval process, that is going to cost us up to 7 extra weeks beyond what we already had worked through with finance. That was not able to start until April 15th. I'll show that when we go through the Gantt chart. So we have started that, but we're in progress, and there's no way that we can finish this on time. I do want to point out that that doesn't mean that we will not make this. We've continued through 3D modeling, prototyping, and making sure that the finance team and executive group has all the information they need from that perspective. And this project is welcome and wanted to finish. But the necessary process has to happen from an auditing standpoint, from a financial auditing standpoint. So I talked a little bit about that recovery plan, or the need to recover. So in order to recover, we continued the design and development of the jig. We finished that. We finished the FEA. Reggie will show us the 3D printed replica of the jig and the fixture, allowing us to do functional testing and to ensure that we have no delays when the finance approval is completed. And then we went as far as we could with the procedural updates and the safety risk assessment. We can't finish that until after fabrication is complete, but John will be able to pick that up with his team after the semester is ended and as they continue fabrication. So with that, I'm going to hand it off to John, and he's going to walk us through the design portion of the jig and the flaps.
Good afternoon, Ms. Harris. My name is Dr. Harris. My name is John Spears, and we worked on a few criteria here for the solution, the Flask Safety Jig design for solution research, the methodology and design criteria, assembly of the drawings, deliverables, and materials and equipment needed. So one of the solutions, or multiple solutions that we addressed, were how do you move the flask from the current foundry through the threshold of the door, past the that's okay, past the capability of the crane. So once the crane gets down the plant and it can't go any further out the door, how do you move the 192 flask through that threshold out into a storage area known as the flask yard? And just quick brainstorming, we came up with a few concepts. One was to use a caster system, or like a trolley system for the flask, where you would bring the flask over, you would set it on the caster, and then you would just roll it out of the door. So a few issues that came up with this is that if you've ever been in a foundry, you would know that it is extremely sandy and extremely abrasive, where you have random pieces of material, metal on the ground, sharp metal on the ground, so tires get punctured very easily. Anything that rotates, that use bearings, the sand gums it up. It creates wear and tear on the equipment. It's very hazardous for mechanical equipment, and so those options weren't suitable for the working conditions of the foundry. A second option that Reggie presented were tracks for the carts. We could just modify a dolly system with tracks. Again, due to the corrosive environment of the foundry, this was not a viable option, because you end up with heavy maintenance on these track systems. Pieces of iron get caught in the gears and the cogs, and it snaps. Belts break. Maintenance has to come down. They spend a day fixing the track or having to replace it. So it's not cost effective, and it's not time effective with maintenance. And we've actually at the plant gone away from the track systems to all wheels, all solid rubber wheels, for that very reason. So that led us to, well, what are the design criteria that we're going to need to meet to move this jig? At our company, we require 5x safety factors. So that means it has to be rated for 5 times the working load limit that before failure. So we are requiring that this jig carry 150,000 pounds, or 5 times the amount of one of the 192 Flask, which is roughly 30,000 pounds. The weight of the jig cannot exceed 40,000 pounds, as the combined weight of the Flask and the platform must be lifted by a 550 forklift, and that has a maximum lifting capacity of 7,000 pounds. So the jig must be sized appropriately and maintain control of the Flask. And if there is a sudden stop or by fork truck, or if it hits a hole or anything, so the center of gravity has to be considered in that. How does it lift? And is it being carried level and securely through the foundry's environment, and also into the unlevel Flask yard? So here's this is the fabrication drawing for the jig. This is the actual final design that we came up with the 2 frames that would run out parallel with one fixed point and one adjustable hook. And essentially what would happen would be you would lay it on top of the Flask with the fixed hook pushed in with the forklift, and then the adjustable hook comes in and attaches, and then you tighten it down through a series of holes and bolts. And then the forklift comes in, slides into the internal tube steel, and lifts it up, and then it's able to move it through. So some of the safety, some of the bill of materials for this jig were that we were trying to use as economical amount of material as we possibly could. No exotic alloys or anything like that, just run-of-the-mill standard fabrication steel, one for use of ease of repairs and just modifications if needed. So we went with just A36 steel. We used 8 1 3/8 bolts and 1 3/8 nuts. We used 16 1 3/8 washers. With that, we used 2 half by 7.5 by 11.25 tube steel, 4 half by 8 by 8 tube steel. The adjustable hook is just a piece of 2-inch stock, and a half by 7.5 by 11.25 tube steel.
Just one thing to point out here, I think, is that total weight of 4,130 pounds is well under the
maximum condition that we have. So we're well below that threshold that we were shooting for. So these are fork extenders. So the forks, we can reach all the way through the entire length of the jig. What this does is it enables us to get to our center of gravity. So the center of gravity is in a prime location for us to lift. Here's a mock drawing of a 192 Flask showing the overall dimensions of what we will be picking up. So what were our deliverables for this? Manufacturing drawings for the jig, on-site fabrication teams, that was completed. The proof that the design meets the safety factor 5X was done and was completed through the FEA process. The process documentations for how the jig will be used with the crane and the 550 fork truck was completed through the, which you will see that on the fabrication drawing. A completed safety risk assessment was completed, and a 3D printed jig and flask as a proof of concept was completed as well. So the implementation plan on this. So once we build it, how do we implement it? How do we get it into use? Upon the completion of the fabrication process and the updated material handling procedure for the 192, material handling team will be trained on how to utilize the new safety jig effectively. Once the team is trained and the new procedure is live, the material handling team will report on a weekly basis as to how the new process is running. If there's any issues identified with this problem, the local management team and supervisors, they'll figure out what the problem is, and they'll issue an update to the procedure accordingly. So the criteria for success for this, what builds the success for this to be used? The proposed design passes the FEA process. The safety team is going to approve that. The fabrication approves that there's no errors in the design or on the fabrication drawings. The fabrication team delivers a complete jig. The updated 192 Flask material handling process, flow, and procedure is approved. The 192 Flask material handling procedure is implemented, including the training and the reduction in overall lead time for the 192 Flask shakeout by 2 weeks. And now I'm going to pass it over to Reggie, where he's going to talk about the finite element analysis that he completed on the jig.
Hello, Dr. Harris. My name is Reginald Hilton. My action items for this project were to meet the goals and objective of making sure that the design that John Spears created passed the SolidWorks finite element analysis test for the jig, as well as to identify any further improvements that we can make to the jig, or at least the process that we were going to use that can be implemented in the future. We also created a document that illustrated the assembling process of my 3D model for the jig itself, as well as a representation of the flask or the item that we were going to be lifting. And we also later created a video of actually showing the jig being used to lift the bottle of the flask and transporting it outside of a facility. As we look at this next slide, we'll notice that the initial design that John presented to us initially, as we're looking at 4 crossbars along 2 parallel long shells, we initially started with just 3 bars, but we noticed through the FEA results that we needed a 4th bar in order to prevent any displacement along the long shells. So even this particular model that we made, which we're calling our initial design, it does in fact pass all of the finite element analysis. You'll notice between crossbars 3 and 4, there is some indication of stress between bars 3 and 4. However, that coloring, if you notice, is not red, it's green, which means that in fact the design as it was did in fact pass. But we did at that point move forward to continuous improvement to see if we could do something better and eliminate some of that green that you see. Next slide, Drew. So here we're still looking at the initial design. Again, it passes FEA, but this particular image is showing us the displacement of the model, where in fact we might have some bending of the 836 steel material. You'll notice that for the majority of the design is the color of blue, which means we don't really have any displacement at all. When you get down to the areas farthest from where the forklift is, it's still not red. You have a light green and getting close to blue. But in terms of displacement in inches, we set the parameters to where we're not even looking at anywhere near 1/8 of an inch of displacement. So our initial design does pass the FEA process. So moving forward into continuous improvement, what we did is we added what you could consider to be extended fork extensions that are permanent to the jig itself. When we did the research on fork extensions only extended approximately 144 inches, and the jig, in fact, is longer than that. So what we did is we placed additional tubing between crossbars 3 and 4, so that we could eliminate the green that was in the initial design. And as you can see from this particular image, we were able to achieve that so that we have blue throughout the entire jig assembly. I'll add that by adding these additional extensions, we also were able to add to the safety factor in that, as John presented earlier, as you travel through this foundry and also get out into the storage area where there's gravel and the forklift may tend to bounce around. Here with these added tubing, the forks can only move so far because they're restricted by this tubing. So we don't risk the possibility of the jig as well as the flask attached actually falling off the ends of the forklifts because they're restricted by these crossbars. So there is still, as you see, a slight bit of displacement at the very end of the jig. But when you look at the color indications using the graph that's to your right in terms of inches, you're looking at something like maybe a 32, 1/32, not any more than 1/16 of an inch of displacement in that area. So our continuous improvement actually enhanced the jig a considerable amount, and quite naturally, it still passes as well. Here, what we're looking at is the bill of materials of the 3D modeling. As Justin presented earlier, we were not in a position to actually fabricate this large jig as it was. So for purposes of our project, we decided to commission a 3D printing company to print the individual portions of the jig itself. When we started this project, we thought that we would be able to print it using a 3D printer at the community college here in Quincy, Illinois. However, the size of the bed was so small, we felt that we weren't going to really get an effective presentation by using such a small bed. So we went to a third-party vendor and had him print the various materials that I would later assemble into both the jig as well as the flask itself. Here you see a representation of the flask that we needed to lift and remove outside of the building. It was so large that we printed it in 4 different portions. And here you're seeing the assembly process. What I used is a glue gun to sort of tack the quadrants into place. And then I used a soldering iron in order to melt the plastic into place, so that ultimately we wound up with this whole item of a representation of the flask that needed to be removed outside of the building. It turned out pretty sturdy. So that was actually effective, at least for our ability to complete a prototype for this project.
Reggie, maybe I shouldn't ask this, but do you have the jig there with you too?
Absolutely.
Okay,
So,
okay. I was like, I know you showed it to us before we got started, so great.
Here we have the representation of the initial jig that John Spears presented. The difference between the initial jig and the continuous improvement is during the FEA, we noticed that along with the deformation, or the possible deformation along the long sill between the third and fourth crossbars. We also had some concerns as to whether these hooks would deform. So in our initial design, the hooks are actually a part of the long sill itself. After doing a continuous improvement design, we then have a design where even even though the hook is still a permanent fixture, the jig still attaches to the flask the same way that John Spears explained it, where the forklift brings it in and this hook is already in place. But we made it to where it's removable. So now, if in fact that stretch that we saw does create some sort of problem uh, years down the line or some significant amount of time down the line, rather than having to replace this entire long shell and rebuild it, which actually would cause you to have to replace the entire build, we can now remove this hook with the two bolts that we have here in washers and nuts and replace them. And here is an example of the hook itself, where the hook slides on, and then it gets bolted as the jig is already on top of the flask. And so ultimately, when we completed the continuous improvement, this turned out to be the best design as we removed the stresses and we made the hooks to where they're all replaceable, given that they were the only locations where we saw any sort of stress and strain in our model.
Great, thank you. So I'm going to finish this up here. I'm going to take us to the Gantt chart here in a second. I'll talk about the critical path, how many tasks we have left. I'll run back through the economic analysis that we completed to show our return on investment, and then we'll close out. So I do need to change screens, so bear with me. Sorry, folks, I have an issue here. Okay, there you are. Okay, sorry. This happens every time I switch over to Microsoft Project for some reason. So as we mentioned before, we did have a bit of a catastrophic event from a timeline perspective, only from a timeline perspective, where we have not been able to complete our planning process. And you can see this final approval for our project ROI, or this finance approval, excuse me, has not been completed. We're about 50%. It was able to start on April 15th. We're looking to finish at the end of this next month. So we're still a month away. That's the typical time. It could end up earlier, but unlikely. But that is holding up. It's a predecessor to many tasks within here, including sending up any parts to the fabricator for the hooks. So you can see we're still delayed for sending that material out. For the actual fabrication team to put the jig together, we can't complete the final safety inspection, the painting, any of the fabrication work. And it's also holding us up on fully updating the procedure, fully completing the risk assessment. Our work as our project team is done, but the folks that would take it from us cannot complete their portion, and therefore they can't train anybody until the jig has actually been fabricated. And so the last few things are going to hold up this project until June 9th. But it's still in the works. It's still, it will be completed. John fortunately works for the company and will babysit this and walk it through. So we're not in risk of that, but we do have that delay. And I just wanted to show through what that looks like on the Microsoft project side, or on the Gantt chart side. So I'm going to go back to our presentation. Bear with me while this loads up for us. Okay, so just to talk about the critical path, We are still on track on the critical path. That finance approval is the next step in that. As soon as we complete that, we can start sending the materials out to the vendor for the hook fabrication. And the fabrication team has already approved the design, so they'll go through and they'll start to fabricate as soon as we know we can spend the money on the fabrication, including the welding, the painting, and then the inspection by the safety team, who will then approve it. We'll be able to put that into production or implement the jig itself and have the final report out soon after. So end of timeline is June 9th. But that it just goes to show that that finance approval is really the, the start and end of the critical path at this point for us. To review the economic analysis, the return on investment has not changed. Even with the an additional cost of having to hire a third party for the 3D printing, we were able to absorb that into our incidental costs that we buffered, that we budgeted for, that 20% buffer right under the subtotal. We had about $1,950 worth of buffer in our project. I mentioned before that the finance approval was new for us. It's because we hit that threshold of $10,000. We were actually almost $1,700 over that threshold, and that's what forced the change in approval process. So the total cost, again, doesn't change. It's just north of $21,678 and change. We did talk before about the revenue increase from a 2-week decrease in process lead time, which allows for an additional part per week to be manufactured. And the team gave us an estimate of about $40,000 per part from a revenue perspective. From a proprietary perspective, we didn't ask for a true figure, nor would we probably get it. We did have to also estimate our profit margin. We did some industry research and identified that the profit margin in the foundry industry is approximately 12% for this type of part. So for that 12% profit margin, due to the revenue increase of $2.08 million, we would be at a profit margin of $249,600 for an annualized return on investment for that first year, for the first 12 months after the jig is completed and the project is completed, of $227,921.60. Then if that continues to the project continues to sustain, you go back to that profit dollar amount, the line above, for $250,000 a year in annualized profit going forward. So that's the end of our presentation. We've covered all of our material, and thank you, Reggie. Reggie's showing us a functional fit of how the jig lifts that really big 3D model of the thing's almost as big as Reggie is in that picture.
If it works there, it works in real life.
That's right. That's right. So I'll say, and I think I speak for the other gentlemen on the team, we had a great time making this. It was a lot of fun, challenging in a handful of ways, but we had a good time. Team worked really well together, and we appreciated the opportunity to present this and put this in front of you. We hope you enjoy it. We will put this out on YouTube. So this video, along with a couple of assembly videos Reggie made, will be out on YouTube. Those will be linked in our final report that you'll be able to see in our submission. So thank you for the opportunity, and have a great day. Stop the recording.